moving on to stationary qubits. Stationary qubits, again, store quantum information in quantum networks. So they don't travel, but rather store the quantum information. They're also used for error correction and entanglement purification as well. Stationary qubits are also used in quantum computers and quantum sensors. And some examples of stationary qubits, again, in the solid state, these include quantum dots, superconducting qubits. So there's an asterisk on the superconducting qubits. These are not typically used currently in quantum networks. They have a short coherence time, or basically time before the noise will destroy the quantum state. And this time is only around 100 microseconds, even with special noise reduction techniques applied. Also, these qubits typically have energies in the 3 to 5 gigahertz frequency range, which corresponds to microwave photons. And it's currently more difficult to convert microwave photons to photons that are in the visible range. And we'll be talking, or in the infrared range. And we'll be talking more later in this talk about why we might need to do this conversion, but this conversion is important right now, and it's a little bit difficult to do with superconducting qubits. However, there's definitely research ongoing in this area. Other types of stationary qubits include diamond defect centers. So in this, the bottom image shown on the right shows a kind of an artistic drawing of diamond defect center quantum memory. So this drawing shows an NV center, or nitrogen vacancy center, which is a color center in diamond where a nitrogen atom will displace a carbon atom in the diamond and create a defect which can emit and absorb photons. The people also will use rare earth ions as stationary qubits, and on the atomic side, people will use cold atoms, hot vapor cells. The picture above the top right picture on this slide shows an artistic drawing of a vapor cell quantum memory. These hot vapor cells are kind of unique compared to these other qubits listed, in that they can actually operate at room temperature. Most of these other qubits require temperatures near 0 Kelvin, or at the very least cryogenic temperatures. So this is really a great property of hot vapor cells. And there's also trapped ions as well, which are used as stationary qubits. So in order to kind of draw some comparisons between some of these qubits, it's useful to look at certain metrics which are relevant to quantum networking. So on this slide, I'll explain what some of these metrics are, and then on the following slide, we'll compare those specific metrics for some of the different types of qubits that we've just discussed. So some metrics that are important for demonstrations of entanglement between two quantum memories include one includes the fidelity of the generated entanglement. So the fidelity will kind of, on the most basic level, the fidelity will tell you how good your entanglement is. So higher fidelity will mean better entanglement. More technically, the fidelity will tell you how closely your quantum state resembles some goal quantum state or some second quantum state. So a high fidelity means the two quantum states match really well, and a low fidelity will mean that they don't actually match very well. Some other metrics which are important, link distance, and of course we would want to have very large link distances, or at least as large as possible, without affecting some of these other parameters, since a lot of these parameters or metrics will be related to each other. There's entangled pair probability, so the probability that you will generate entanglement. This we would want to be higher, of course. There's also entanglement rate, basically how often per second you're able to generate entanglement. and we would of course want this to also be as high as possible. And then there's also wavelength. So this is just referring to what is the wavelength of the photon, or what is the wavelength of the photon that's emitted from the stationary qubit, which basically corresponds to that energy of the energy difference in the stationary qubit. So we'll also be talking more about some of the kind of pros and cons of using different specific wavelengths, and also where transducers will come in there. So this slide shows a table comparing some of these metrics that we just talked about for entanglement established between two nodes. These are all kind of very recent experiments, so obviously research is ongoing in this field, and none of these metrics are necessarily set in stone, but this just gives a sense right now of where we're at, kind of state of the art for some of these qubits and for some of these metrics. Also, this table is taken from a recent review, which you should definitely check out if you're interested. So from this table, we can see that there are kind of varying fidelities that have been achieved, varying with what kind of widely varying link distances that have been achieved, and also varying entangled pair probabilities that have been achieved for some of these different platforms. We can also see that the wavelengths that correspond to the different platforms or different types of stationary qubits are mostly around the visible and infrared range.